We've previously stated that linear regression is one class of machine learning problem, generally referred to as function approximation. And function approximation is actually a subset of supervised machine learning. So in a nutshell, what linear models try to attempt, or what function approximation models in general try to attempt, is to come up with a function that links two variables together. One of these variables will be the one that we are interested in predicting, and the other variables are the ones that contribute to the change in such variable. In machine learning terminology, the variable we are interested in predicting is called dependent variable, and the variables that contribute to the change in that dependent variable are called independent variables. So how does the linear model comes up or calculates this function? This is what we are gonna learn in this video. Let's learn some basic linear algebra terminologies, and if any of this doesn't make sense right away, just power through it and it will all make sense at the end. Let's start by vectors. And to keep things simple, let's consider vectors as a representation of numeric data in arrays. In general, vectors are a special object that can be added together and multiplied by scalars. And scalar here means a number, so whenever you read the term scalar, it represents a number or it means a number. Vectors are represented in ND arrays in Python using the NumPy module, and let's call it V. If you want to know the dimension of a vector, we can use a shape, so v.shape. We can see it's 4, and this number here represents the rows. If there was a number here, it represents columns. Single vectors are always represented as one-dimensional arrays in Python, and it just basically says that it's a row consisting of 4 values. We can multiply a vector by scalar, so if it broadcasts the arithmetic operation to each element in a vector, so we can see here that 2 is multiplied by each element inside the vector. We can also transpose a vector, .t means transpose. However, this is not gonna produce a different vector than the original one, because we said that single vectors are always represented as one-dimensional array, so it basically does nothing. We can multiply 2 vectors together. The multiplication also took an element-wise operation, multiplying each element, the ith element in each vector, like the ith element in the other vector. So 2 multiplied by 2 is 4, 4 multiplied by 4 is 16, and so on. We can also add 2 vectors together. Similarly, it's done element-wise, so 2 plus 2 equal 4, 4 plus 4 equal 8, and so on. We can calculate the length of a vector using norms. So norms are basically the length or magnitude of a vector. If you want to calculate the absolute norm or L1 norm for our vector, we basically calculate the absolute value of our vector. Since we don't have any negative ones, we produce the same amount as, or the same result as the original vector, and we basically sum. So we represented our vector using a single number being sum of absolute vector values, and this is called L1 norm. This is basically if we want to compare 2 vectors together. So let's say we have another vector, v2 for example, and let's calculate the L1 norm for that vector. So we see here the benefit of calculating the absolute value of a vector is that it ignores the negative sign and computes only the positive values of this vector, so we can compare 2 vectors together. There are another type of norm that we can calculate for vectors, which is L2 norm, also called Euclidean norm. It's basically square root of the sum of squared values inside the vectors. This is another calculation of the length or magnitude of the vector. Each has its own pros and cons, but just know that norms are representation or calculation of the length of a vector, and it can be used to compare, for example, 2 vectors together. We have previously multiplied 2 vectors together, produced another vector, including an element-wise multiplication of each element of the vector. Now, if we want to summarize this in a single number, we can sum the result of the multiplication. So 81 is the summation of element-wise multiplication of 2 vectors together. This mathematical notation is called inner product or dot product, and it can actually be represented by using the dot method. So if we say v, which is the first vector, dot the second vector, we get the same exact result. If we have multiple vectors inside the array, this is called a matrix. So this shape here is called a matrix, and if you look at closely, it looks like a table, and matrix is simply a group of nested vectors together. If we want to understand or look at the shape of the matrix, we can use also dot shape. Matrix has two dimensions, rows and columns. And in our case here, the matrix consists of 3 rows. Here you can see 3 rows and 4 columns. We can actually perform a transpose on matrix. It switches rows with columns. So we can see here transpose did produce a 4 by 3 matrix, 4 rows, 3 columns. And if you look at the shape of the transposed, we can see here that it switched the rows with columns. Before we go any further, how does this representation of data fits into our insurance data? Simply, if we look at our data, we have our table here, and if we consider this table in matrix and vector notation, we can consider this complete table as a matrix. It's a 1300 by 7 matrix, and if we think of a charges column only, it can be considered as a vector. So we can say that our matrix X, and matrix is always represented by a capital letter, is df.drop charges. So our X matrix, it's all columns except charges, and our Y vector to be the charges. If we look at X matrix, it's all the demographic characteristics of the customers, and if we look at Y vector, it only denotes the insurance charge column, the dependent variable that we are interested in predicting. We can also present these tables or data frames in form of array, and it forms a nested array similar to what we have discussed earlier of all the data inside our table. Similarly, we can do this for Y. We can see here also that charges became one-dimensional array. Now let's get back to our earlier example. Let's look at our vector and matrix. So we have a one-dimensional vector of 4 elements, and our matrix consists of 3 rows and 4 columns. We can do a matrix vector multiplication simply by using the dot product. What actually happened here, it multiplied each element in a row by a corresponding element in the vector and summed the multiplication results. So we know that dot product is the sum of multiplication of ith element in each vector or matrix, and this is what actually happening here. To perform this operation between a vector and matrix, the dimensions of the columns in the matrix should correspond to the dimensions in the vector. So we need to have the last dimension of the matrix, which represents the column, corresponds to the same, exactly the same as the dimension of the vector. If these two were not equal, this dot product cannot be produced. So for example, it will produce an error because it says 3, the matrix is 3 by 4 and the vector is 3, not aligned. So we can't actually perform a multiplication with vector and matrix that are not having the same dimension in terms of matrix columns and the rows in the vector. If we go back to our earlier example and perform our dot multiplication, it runs without problem. So we can actually also do a matrix by matrix multiplication. We created another matrix that is 4 by 3, 4 rows and 3 columns. We can actually employ the same dot product operation as we did previously between matrix and vector. We can do the same between matrix and another matrix. And also we need to understand that to perform this operation, the number of columns in the first matrix need to correspond to the number of rows in the second matrix. So if any of this does not match, it will produce an error. And when we do the multiplication, the dot product, it produces a 3 by 3 matrix or whatever these numbers were. So if we denote the number of rows in the first matrix to be n and the number of columns in the second matrix to be k, when we do a dot product, the result is n by k matrix. We can see here that it produces a 3 by 3 matrix, which is a dot product of these two matrices. Let's talk about identity matrix. Identity matrix corresponds to the number 1 in the real numbers. So if you multiply anything by 1, it produces that same anything. So if we multiply 2 by 1, it produces 2, 3 by 1, it produces 3. Similarly to identity matrix, if we multiply a matrix by an identity matrix, it produces that original matrix. So to create an identity matrix, we use numpy.i. Let's make this I 3 dimensions. We have created an identity matrix with dimension 3 by 3, 3 rows and 3 columns, and we can see here that one characteristic of an identity matrix is the 1 at the diagonal and 0 elsewhere. If we multiply, for example, our V matrix by, let's call this I, okay, I for identity, it produces the original matrix. Now let's talk about the inverse of a matrix. Similar to what we've done in identity matrix, when we multiplied an original matrix by identity matrix, it produced that original matrix. If we multiply a matrix by its inverse, it produces an identity matrix. So if we want to cancel two matrices together, we multiply a matrix by its inverse to produce an identity matrix, which is basically equals to 1. The problem is that not all matrices have an inverse, and only square matrix has inverse. And what is a square matrix? If you recall our M matrix, it has a shape of, also this is not a square matrix. Square matrix is a matrix where number of rows is exactly equal to the number of columns. If we want to select a portion of this matrix to make it square, we select the first row. We know that Python is 0 indexing, so if we want to select the first row, we access it by 0, second row and third row. Let's look at our new matrix. This is a square matrix. If you look at this shape, it's 3 by 3, 3 rows, 3 columns. To inverse a matrix, we use numpy.linealg. Linealg stands for linear algebra. This is where we can do a lot of linear algebra operations on matrix and vectors. Dot inverse v. So this is the inverse of our new matrix. Now let's call this v inv. And the dot product of a matrix and its inverse is an identity matrix. For example, this portion here evaluates to 1. So if we have a matrix at one side of an equation and we want to cancel this matrix, we figure out the inverse, then multiply the matrix by the inverse. So it evaluates to 1 and the matrix is cancelled from this side. What's really important here is to understand where does all this fit into linear models and machine learning in general. We previously represented our data, the table of insurance charge, in the form of matrix and vector. We know already that the linear equation is represented as follows. Here the dependent variable is y is actually equal or approximately equal to a linear combination of model parameters denoted by beta, so this is beta 0, beta 1, beta 2, and feature values. For example, first feature, second feature, and so on. What is actually this beta and feature thing is? Feature is in the context of insurance charges, for example, this will be the age of a customer or number of children, gender, whatsoever. And beta are the model parameters that the linear model actually estimated. So this betas are the estimate of the model, and these are our features. And our dependent variable is a linear combination of model parameters multiplied by feature values. This term here is the error term. It's basically the difference between the actual and predicted values, and this whole equation here is the solution that minimizes this error term. So the summation of all these parameters together presents the lowest or the most accurate value of y. We can simplify this equation and represent it in the form of a matrix and vector notation. So we will group all the axes or the features in our X matrix, and we saw that X matrix is the demographics of all the customers multiplied by the model parameters. And ignore this for a second. So you can say that Y, the insurance charge or the dependent variable, is actually the dot product of a feature matrix and the corresponding model parameters or betas. So this is actually how predictions are made. So when we call a model and fit our data to the model, then request a prediction, this is what actually happens. So predictions are actually the dot product of a feature matrix and model parameters. So this is one side of what's happening. The other side is how does the model actually estimates these betas. We will try to approximate what's actually happening in the estimation process, and I'll leave a link for you to go through if you want to seek a proof for what we are going to discuss here. So in order to understand how these betas are estimated intuitively, we know that Y or dependent variable equal to the dot product of feature matrix and betas. So if we want to isolate the beta or isolate this side to calculate or to estimate the coefficients, we can multiply this side by the inverse of the feature matrix. And we know that when we multiply a matrix by its inverse, we get an identity matrix, and identity matrix equal 1. So if we multiply it by the inverse of x, we will cancel x from this side and we will be left with beta. So beta would be equal to x inverse multiplied by y. But unfortunately, x inverse doesn't always exist, and x is rarely invertible because simply we said that all or almost all square matrices are invertible, and in most of the cases x is not a square matrix, so there is no inverse for such matrix. To try to inverse the X matrix, we multiply first X by its transpose, and when we multiply X by its transpose, it results in a gram matrix, and the gram matrix is just the transpose of a matrix multiplied by itself, for which an inverse usually exists. So when we multiply this side by its transpose and multiply this side by its transpose, so it will be XTXB here in this side. It will be XTX, transpose X coefficients, equal to XTY, the transpose of the matrix by the actual Y values. The last thing to do here is to multiply this side again by the transpose of this matrix in order to cancel this whole matrix from this side, and beta will be equal to X transpose X multiplied by the inverse of the gram matrix. So basically the solution for beta is an inverse and transposing the actual matrix to isolate beta and solve for it using the solution we just discussed. It's called the normal equation, and I'll leave a link in the description box so you can follow along. To summarize this, when we call a linear model, the model estimates the coefficients or the betas using this calculation that we've just discussed, then generates predictions or approximation of Y using the matrix and vector multiplication we discussed earlier. To apply all what we have learned so far, let's make a simple example of a linear model and observe these calculations in action. Let's, for example, say we have X matrix consists of feature values. Let these features be, for example, age, children, gender, whatsoever. And we have our beta 0, which is the intercept. And we have our weight vector. And weights are the coefficient or the estimates that the model produced. To generate prediction, we simply say that predictions equal to weight 0, the intercept, which is here, beta 0, plus the dot product of a matrix and the weight vector. And when we run this, it will produce 85, which is actually the prediction for this current feature set. Now, if we want to express this notation in a simpler form, we will include the intercept inside the weight vector. And now we can simply say that prediction is a form of the dot product of feature matrix and weight vector. It gave the same exact solution. This will also hold true when we add more observations to our feature matrix. So let's consider that each vector in our matrix represents a single sample. So for example, this are the feature of a single customer, and if you want to add more customers to the matrix, we can simply include them in the matrix. And now using the same concept, multiplying the feature matrix by the weights vector, and note that each vector in the matrix represents a specific demographic characteristic of a customer. Now when we run this, it produced prediction for each customer, and let's pretend that these predictions are the insurance charge that represents or relates to this customer. To understand what are we doing here, guys, we are just mimicking what happens when we request prediction to be generated. And we are just discussing what we explained previously, that prediction is just a matter of matrix and vector multiplication between the feature matrix and the weights vector. And this is what we are actually saying here. Our X matrix is the demographic characteristics of customer. Let's pretend that this is the demographic characteristics of the customers, and this is the weights that have been calculated by the model, and prediction is actually the dot product of weights and feature matrix. If you recall, we said that not all matrices has inverse, so our X matrix here is not a square matrix, so it doesn't have an inverse. We see it's not square matrix because square matrix is when number of rows equal to number of columns. If we try to invert this matrix, we will get an error that says last two dimension of the array must be square. So it basically telling you that this matrix is not square matrix and there is no inverse for such matrix. So to try to inverse this matrix, we can transpose first the matrix, then try to find an inverse for such matrix. But we said that it doesn't always work, and we'll see why it doesn't always work. So for example, if we transpose the matrix, so x dot t transpose dot x, this is a gram matrix. Now let's try to invert this gram matrix. We will get also an error. To understand this better and what does actually a singular matrix mean, we need to calculate the determinant of a matrix. It should be equal 0. If a matrix has a determinant of 0, it means that it is not invertible. So what does this singular matrix actually mean? To understand singular matrix better, or why we were not able to invert the gram matrix despite being a square matrix, let's visualize our original matrix, the correlation in our original matrix as follows. So we will create a data frame from this matrix. Remember that we have included an intercept or constant, and we want to visualize only the numbers excluding the constant. So we first select all the rows, as we didn't specify a specific indice, so this means that we select all rows, and when we start to selecting columns, we start from the first column. It's a perfectly correlated matrix having a positive correlation of 1, which simply means that features are highly correlated with each other. And sometimes we are not able to invert the matrix when features inside the matrix are highly correlated with each other, or when the determinant is 0. You need to be especially aware of this correlation between features because it can mess up the calculation of the regression model. And we will see later how can we test for this. So we have seen how to generate predictions. Now let's make an example of how to calculate coefficient vector in the first place. Let's use the same matrix that we were not able to invert. This time we are going to try to invert it using a less correlated features. We said that we were not able to invert the gram matrix because of many reasons. One of them being multicollinearity, and multicollinearity is simply high correlation among each feature. Before we go any further, let's first calculate the gram matrix and check whether we can invert it or not. So our gram matrix is xtx equal x dot t dot x. Let's try to invert this gram matrix. It didn't produce error. This means that our gram matrix is actually inverted. Let's have a look at our original matrix using the same approach we did earlier. We can see already that not all features are highly correlated with each other as they were before. Having a multicollinearity among features can impose problems. So this is something that we need to check for when we run a linear regression, and we will see how we can assess and calculate multicollinearity later on. Let's recap quickly what we have here. We have our X matrix, we have our Y vector, and we have calculated our gram matrix, inverted our gram matrix, and now it is time to calculate coefficient or estimates of a linear model between this feature matrix and Y vector using the normal equation. So our weight vector will be simply the normal equation x dx inv dot x dot t dot y. And now let's look at our weights vector or coefficient vector. This will be our coefficient vector. Here we have, of course, we are using numbers for just demonstration, so don't take these numbers seriously, but this is the intercept, and this is the weight for the first feature, and this is the weight for the second feature, and this is the weight for the third feature, so on, so forth. So the first number in each feature is the intercept, okay? The second one represents the value of each feature. For example, let's denote that these are age, for example. The third one is, for example, relating to number of children, so on, so forth. So by now we understand how to calculate or how weights are calculated using the normal equation, which is basically a form of matrix and vector multiplication using inverses and gram matrix. And we also know how those predictions are generated. Let's use what we have learned so far in coding a linear regression from scratch using our insurance dataset. So let's first instantiate our X matrix, and let's select the numeric columns only. And our Y vector will be df.charges. Let's look at our X matrix. So it's age, be my children, and if you look at Y, it is the charges. Now let's take all the equations that we have done here. We don't need this. Okay, this is a very naive error. We have selected the smoker group, but we have selected all the values of Y from the original dataset, not the smoker group only. So we'll simply use this and use the charges column. In case you're wondering, first we make a selection for a specific portion of the dataset, and then we select the column that we want to display. Now let's run this cell, and let's look at the weights. Note that we haven't included an intercept, so let's include an intercept in this matrix. So we here have the intercept and the coefficient values. Let's rerun this exercise using the modules to double check our calculation. So we will use a stats model. We have the exact same results. Basically, all coefficients are exactly the same. So congratulations, guys. You have coded a linear model from scratch using linear algebra. It's actually celebration time, but before you go, and because I like you for continuing and sticking around this far, you have earned a bonus. If you use chapters, you haven't earned this bonus. Be honest, go back and watch the video from start. We have several other topics to cover that will also be helpful in your journey to understand machine learning and what's actually happening inside the models in general. So we have previously seen that the matrix we used in the earlier example, we were not able to invert this matrix because we said there is a high multicollinearity among features. So let's try to understand what is multicollinearity better, and so far we have also been using numeric features only. So let's try to use a categorical feature in the model. We will discuss the concept of multicollinearity and how to use categorical features in one example. But before we actually do this, let's make predictions. We said that prediction is a fact of weights multiplied by a feature vector. So to calculate the prediction for our model manually, we have our weight vector, and we can simply use the dot product. So let's, for example, say spread equal x dot weight. And let's look at prediction. And let's compare our predictions to the one generated by our model. So model.fitted values is exactly the same result. So we now understand that prediction is a matter of the feature value multiplied by the weights vector. Let's incorporate categorical feature into our model. First, let's look at our data to just remember how did it look like. So you see here that categorical features are included in a string format. We can't actually pass string format to the model. The model doesn't interpret categorical feature like this. So we have to encode this to a numeric version. To do this, we use one-hot encoding, and one-hot encoding simply divides this categorical feature into two columns using 0 and 1. For example, we denote females to be 0 and males to be 1. In case of a sample that is female, the column will indicate 0 and males it will indicate 1. So one hot encoding create as many columns as inside the levels of the feature denoted by 0 and 1. So for gender there will be 2 columns, and for region, for example, there will be 4 columns. There are several ways to do one-hot encoding. We can actually use pandas. So we see here that it expanded our original feature matrix and included, for example, gender, divided it into 2, one for female and one for male, similar to a smoker group and for a region group. And we can see for region group it created 4 different columns, and one-hot encoding will create as many columns as there in your categorical levels. Let's check the correlation of this feature matrix as is. This is the heat map, and I want you to check this portion of the heat map. So we can see here that smoker no is highly correlated with smoker yes, and this simply means that these two features, or the newly created features from the get dummies, can be inferred from one another. So if a sample is marked as 0 for non-smoker, it goes without saying that it is a smoker, because there is either a smoker or non-smoker. And this is an example of multicollinearity among features. To avoid this, when we create categorical features, we drop either one of these columns. Drop first means drop the first category. So if we have 2 categories in gender, for example, male and female, we drop one, either male or female. You can see here we have only 1 representation for each gender, 1 representation for each smoker, and 3 representation for the region feature. And when we come to look at the heat map, we see here that the highly multicollinearity among the smoker group is actually gone. This is actually one way to represent categorical features using one-hot encoding. Another way to do this is to use dict vectorizer. Now we have to represent our data in form of dictionaries to pass it to the dict vectorizer. So we see here for each row, it created a given dictionary, and for each dictionary we see that age has its own value, gender has its own value, and so on. So rows are actually the inputs to this dictionary. Now we are ready to pass our data to the dict vectorizer. We can simply use dict vectorizer.fit transform our dictionary record. You know already that fit is where the calculation happens, and transform is where you apply this calculation to whatever you pass. So it created an array of the values, and it already changed the categorical features into a 0 and 1 representation. So it leaves the numeric feature as is and transforms the categorical feature into numeric representation. This might not be actually visible here, so we can create a data frame from this dict vectorizer. Let's see what did it actually do. It left the numeric variable as is. Remember that we did pass all features, numeric and categorical features, and it automatically left the numeric feature as is and assigned each categorical feature to its numeric representation, being 0 and 1. But again, also it did not drop one of these columns. similar to what happened earlier when we run get dummies for the first time. So we need to be aware of this, and we need to remove one of these features if we want to continue using this type of encoding. Now, if you recall, when we did our crosstabs earlier, we said that region is actually not that significant, and just only because the existence of a smoker group or concentration of smoker group in southeast region is what's making it significant. We want to test this. Let's first regress charges to region only and add smoker group, then remove region and observe the difference. We get a very small r squared and insignificance in region feature. Now, if we include gender and smoker, we'll see increase in the model performance, but actually still region is insignificant, and also gender is insignificant, and smoker is actually the most significant feature. So if we regress only on smoker, we'll see that it's almost the same result without having any difference when we included all these features. And if we look at the model, we have a normally distributed residual, and we have also almost no heteroscedasticity issues. This highlights the importance of doing an earlier analysis and understanding features to know what actually should you include in your model and what to exclude. Lastly, the aim or the main goal of machine learning is to make predictions using historical data on unseen data. And what we have been doing so far is that we are using our same data to train the model and also to test the model, which is not efficient because we are actually by this ensuring that the model memorizes our data without testing the real ability of the model on unseen or new data. So how to do this? If we want to assess the model performance and we want to test the generalizability of our model, we need to test the model on unseen data or new data. And basically, this is the data that the model hasn't seen during training. So we actually can use a separate data for training the model and another data set for testing the model. So from sklearn model selection, import train test split, and train test split is where we split our data into training set and testing set. We are going to split our dataset in two portion for training and portion for testing. So here basically we will have two sets, one for training and it has its own x and y, and one for testing and it also has its own x and y. So train test split, what are we going to split? We are going to split x and we're going to split y. We are going to pass the x and y, but we are going to pass them not in the form of data frame, rather in a form of array. Now when we instantiate our model, we will pass the training set only. How to assess the model performance on the test set, and it's sometimes called out of sample performance. How to do this? We will make predictions for test set first, and to assess the performance of the model out of sample, we need to compare it to the performance on the training set also. Now it will be actually good to look at how do we calculate R squared that we have been using since the start of our demonstration. So R squared is basically the calculation of residual sum of squares divided by total sum of squares, and it might sound complicated but it's actually not. Remember that linear model, and specifically ordinary least square model, minimizes the residual we discussed earlier, and this residual is the difference between the actual data points and the fitted line. And as the line moves up and down, we see here that the residuals increase or decrease, and the best fitting line is the line that actually maintains a minimum residuals across all the data set. Okay, so what are residuals? Residual are the difference between the fitted line and the actual data point. And what is the fitted line? Fitted line is basically the predictions created or generated by the model. First of all, let's calculate the residual sum of square. We'll do a list comprehension for this. So we start list comprehension by an empty list, and we will use I minus j, okay, squared. Okay, what is I and what is j? For I, j in, we need to subtract predictions from actual values, then square them. So Yeah, okay, I forgot something. So we said that I and j in Y train and pred train. So these are actually two lists that we passed. In order to combine two lists together for the iteration to work, we use zip. So zip makes sure that iterates over each i's and j's element at each of these passed two iterables at the same time. So we get this huge value. Let's call it a residual sum of squares. Now let's compare this to the total sum of square, and total sum of square is basically I. This time we are gonna use the average of y. We are simply comparing our model here, and our model here is replacing the average, and we said that the average is the expected value of something and it's actually a prediction. So the model replaces the average with a better calculated value as we saw earlier. So if our model does not explain variation better than the average, we are better off without this model in the first place. So we have our RSS and TSS. Now let's actually calculate R squared. It will be equal to 1 minus RSS divided by TSS. And we have here a major problem that we are calculating on test set and actually comparing to the train set. So we need to use test. Okay, so everything looks fine. And let's calculate the R squared. It's 77 or almost 78. It is basically the percentage of variation in the dependent variable that is explainable by independent variables. So we can actually use sklearn to calculate the R squared. So R squared is similar to what we have seen earlier. So for test set we have a 77 R squared, but when we calculate this for train set, we are now comparing the performance of the model on the training data and the performance of the model on testing data. R squared here, the manual is calculated for test data, and the one from sklearn will be calculated on the training data. It's 74. So we have actually an improved performance on test data, and having an improved performance on test data doesn't necessarily mean that the model is actually performing good. It might mean that data in the test set is much more easier for the model to interpret. We have used a single dataset for training and a single dataset for testing. So there might be some sort of bias. The training set is much more difficult than the testing set, or vice versa. As a rule of thumb, we usually want to see similar behavior or performance between the train and test dataset. When we see that the training set has much more better performance than the testing set, this means that the model overfits. And what does overfitting mean? It means that it learns the data in training set or memorizes it in training set, but it fails to perform on unseen data. And this actually has a lot of discussion to go through to handle overfitting. But in general, what we want to understand from this exercise is that to make predictions, we want to ensure that our model has a generalizability on unseen data, and one way to test this generalizability is to use different sets for training and testing our model. Instead of using a single train or test set, we can use different sets. So for example, if you recall, when we specify random state, or when we took a sample from the dataset earlier, we used random state. And random state, because this splitting happens randomly, it specifies a fixed point to create the same exact split each time this code is run. So if we change the random state now to 2, for example, this means that these sets are going to change, and of course might affect the calculation of our performance matrix. Now our R square from the test set decreased slightly. Previously it was 77, now it's 76. And if we look at the training set, it's also the same 74. So what does this random state do? It actually changes the sample composition of the training and test set, and we see here that it's reflected in the scores. If we use another data set, another number means that these sets are actually changed again. Now it's 68, considerably different than what we have seen earlier. And let's see the score. So it's actually 77. So one set we had an improved performance, another set we had a bad performance. And this, what we have done here, is called cross-validation. Instead of using a single or a fixed train or test set to assess the model, we use different sets. And cross-validation simply, instead of splitting the data like this, it splits the data into k-fold splits. So for example, it makes 10 splits and train the model on 9 portions of the data or 9 splits and test it on the 10th one, so on and so forth. Then averages the performance across all test sets and give you a final R-score result. So it will be better and less optimistic than what we have done here. If you are wondering what does this equation actually mean, it's basically calculating the percentage change between RSS and TSS. You know that in RSS, residual sum of square, we substituted the predicted value or the mean with our model. So we want to understand what change did this substitution bring, and it's basically we want to calculate the change in the residuals after introducing our model. To understand this better, we can redo this calculation in a simpler way. First, we subtract RSS from TSS, and this basically identifies the change that our model introduced, because the residuals after introducing our model is less than what it has been before our model. Now, if you want to calculate the percentage change, we simply divide by the TSS. So we can see here that it's exactly the same calculation. And what does this actually mean, this negative 68? It means that our new model is able to explain the variance, which is here, difference between each observation, square difference between each observation and its mean. So our model is able to explain the variance by an amount of 68%. Where does this 68 come from? It's basically the difference between our model and the random guess divided by the total residuals or errors. And if you want another interpretation for it, we can look at it from different perspective. If we consider the new residuals in relation to the old residuals, we can calculate the percentage. So RSS divided by TSS is 31%. So our new residuals, which is the difference between actual values and our model predictions, represents 31% of the total variance in the data. And the total variance is basically the difference between each value and its predicted value, the simple mean. So this means that 68% were actually removed from the total variance by our model. This is simply the added value of our model compared to a simple average. Just subtract 1 and we get the calculated R squared. I hope this makes sense. In a nutshell, R squared is the percentage of explained variance by our model. Another matrix that we can use is the mean squared error, and mean squared error is basically the difference between, or the average squared deviation of predictions from the actual values. So we have this actually calculated here, the sum of square deviation of prediction and actual values in RSS. So we can basically say that MSE, mean squared error, equal RSS divided by length, because it's the average length of Y test. And let's look at the MSE. We see that it's actually a big value and big number. And if you recall from the variance calculation that we have discussed in descriptive statistics earlier, if you haven't seen this, I suggest that you go and check this video out. That because it's squared, it has a high magnitude. But if you want to express this variance in same units as the charged value, we use the square root. So root mean squared error is basically numpy dot square root MSE. We can see that it's around 6k, so there is a 6k positive or negative variation in the predicted amount for a single customer. Another property, or what's important to note here, that we can compare these two matrices to the actual variance and standard deviation in the dataset before running our model. So we can calculate the variance. This is actually higher than this. So let's compare the standard deviation. we can see it's actually 11K, and this means that our model is performing better than a simple guess, because we know that standard deviation is calculated using the average, and average is the expected value of a given amount. So our model is performing better substituting the expected value by predicted value using model parameters. Similar to what we have done with R-square, we can calculate mean squared error using sklearn. Mean squared error, let's pass the y-test and thread test, giving the exact same results, and we can compare also square root. So we have the exact same result using sklearn module. Basically, if we change also the setup here, so let's make this 2 and run after, lets you run all cells after this current cell. So run after, we run everything using a different sample. We can actually see we have a better R score, 5.9K. I think it was earlier 6 point something. The model is currently performing better than earlier, but we know that this is actually optimistic because we are using a single test set, and we know how to handle this using cross validation. One last thing to wrap this intro to machine learning is the example of a single linear model and understand what does coefficient really mean. Remember that up to now we have been using multiple linear regression, which means that we've been using several input features like age, gender, so on, to estimate the dependent variable being the insurance charge. In single linear regression we use only one variable, so let's consider the BMI for instance, and we can calculate coefficient by another simple calculation being covariance divided by variance. This is the covariance matrix, and the actual covariance is this number here. So we select the first input and we select the second number. Okay, so this is the covariance, and we simply divide by variance, and this will actually be the coefficient of BMI, using only BMI as a single feature to predict the charges. Now if we use, for example, statesmodel.ols, df.charges, df.bmi, can see here that BMI is almost equal to what we have calculated earlier. So in a nutshell, from this simple calculation we can understand that a coefficient indicates the degree of association between two random variables. That's why when we express or we interpret coefficient, we simply state that for a 1 unit increase in the independent variable, we expect that the dependent variable increase by, in our case here, 394. So hopefully by this you have understood linear models and machine learning a bit, and now when you run this single line model you will understand what's actually happening under the hood. See you next.